Problem number 3 states, the moon is slowly moving away from Earth as the Earth's rotation slows down due to tidal forces. They want us to find an expression for the angular momentum of the moon as a function of its mass, little mm, the mass of the Earth, big M-E, the gravitational constant G, and its distance from the Earth, Rm. They want us to explain qualitatively how angular momentum is conserved as the moon moves farther away from the Earth. And they've given us a hint to use Kepler's law in the form of angular velocity squared equals the gravitational constant times the Earth's mass over the distance from the Earth cubed, or velocity squared equals the gravitational constant times the mass of the Earth over r, or over distance of the Earth. So the first thing I've done is just written down the equations that were given to us, and then I've drawn out a little figure here showing we have the mass of the Earth, distance r from the moon, which is being pulled towards Earth by the force of gravity and moving in a orbit around the Earth. So they want us to find the angular momentum of the moon. We know angular momentum can be found using the moment of inertia times the angular velocity. We have angular velocity squared here, so we can just square the rest of these and then use this to find our angular momentum because we have the moment of inertia of the moon. We know it's equal to mr squared because we have a mass, distance r from the axis, rotating around the axis. So we can take our equation and then we can just multiply it by I squared on either side. And since we know the I squared, we can plug that in here. Since we know that I times W squared is equal to the angular momentum squared, we can just now plug in that angular momentum. So the angular momentum of the moon squared is going to be equal to this here, and then we do some algebra, and we end up with the angular momentum of the moon equal to the mass of the moon times the square root of the gravitational constant times the mass of the Earth times the distance from the Earth. And they want us to explain how the angular momentum is conserved as the moon moves farther away from the Earth. So using this, sorry for my shaking, using this, well, either of these actually, we know that if the moon is slowly moving farther away from the Earth, we know that this distance here, this Rm, is going to be increasing. So if this is increasing, this will be decreasing because this is actually the square root. So as r increases, angular velocity decreases, and as angular velocity decreases, we know the moment of inertia is going to decrease. So the moment of inertia, the angular momentum is going to decrease. So the angular momentum of the Earth is actually decreasing as the angular momentum of the moon increases. And so, yeah, so that's how the momentum is conserved in the system.